Well, tonight I wanted to go over our indefinite integrals and just go over a lot of our basic rules and just really work on mastering and dominating this particular topic. And we'll get into some specific examples to make sure we've got it all tied together. The first rule I want to go over is our power rule. And basically the power rule says if you're integrating x to the nth power, and then there is that special note that says, hey, don't forget n cannot equal -1. If it does equal -1, that's an entirely different rule that hopefully you already know. But anyway, as long as n is not equal to -1, we're going to say the antiderivative is x to the n plus 1 divided by that new exponent itself plus c. And then we're going to get into all our trig ones, and we're going to cover these. And normally we would just do the integral of cosine of x, and we would say that the antiderivative is the sine of x plus c. But I want to take it a step further today with all of our trig integrals, and I want to include a small inner function, ax. So you've got the variable x and a constant a, and the antiderivative would be 1 over a sine of ax plus c. And so I'm just going to include that on all of our trig ones. And I'm going to go ahead, I'm going to write out the next 5 that I want you to be able to practice fluently, and then we'll go ahead and have you try them on your own. Alright, so here's the next 4 that I want you to be able to go over fluently on your own. And oh goodness, I feel like I am forgetting one here, but maybe we've got them all covered. Anyway, so good luck. See if you can fill in these 4 particular ones, and we'll come back and check our answers. Alright, yeah, I was forgetting one at the bottom. I just snuck it in on the screen now. Cosecant of ax times the cotangent of ax. But anyway, starting back up here with the first one on the screen, the antiderivative of sine is going to be negative cosine. Whoops, I already forgot my coefficient. -1 over a cosine of ax. So that was one of my big things, is just being able to watch our signs as we go through this one. The antiderivative of secant squared would be 1 over a tangent of ax. So basically what we're doing is we're hitting a little miniature u sub on all of these. On all of these we're letting u equal the ax, and we know that we're going to end up with a coefficient of 1 over a by the time we're done on all these. Number 5 here, I've got 1 over a secant of ax. And let's see. Okay, I got to watch my signs here on these last 2. The antiderivative of cosecant squared, -1 over a, and let's go cotangent of ax plus c. Yeah, these last 2 are the ones that are very rare, and -1 over a, and this would be cosecant of ax. So we have seen these show up on the last couple of Regents exams, and we just want to be ready in case we see them again. Couple more basic rules. I want to talk about integrating du over u. I want to talk about integrating e to the u with respect to u. I also want to do the antiderivative of tangent of u. And also, let's see if we remember the natural log of x with respect to x1. So go ahead, try those 4 again, and come on back, see if we agree. Alright, for du over u up here, I said it's the natural log of the absolute value of u plus c. Absolute values are very important. E to the u is our favorite one. It's just e to the u itself plus c. Alright, now tangent. Now, don't sweat. If you can't memorize tangent, it's not a big deal. We could always rewrite it as sine over cosine and let u equal the denominator and work our way through it, but there's 2 alternatives that we ended up with. We ended up with negative natural log of the cosine of u. Or we could say that -1 is, instead of being a coefficient, can be moved to the exponent, and cosine to the -1 power is the secant of u as a power. So those are the 2 options there. And then for number 11, we used to do parts, integration by parts. We used to let dv equal the dx. We used to let u equal the natural log of x, and we worked through all that integration by parts. But here's what we got each time. X times the natural log of x minus x plus c. And that's become a fairly common one that I know most of you have already memorized. So I think we're ready. We've covered all our basic rules. We've got 11 of them so far. Let's jump in and try a couple. All right, I've got 5 specific examples for you to try tonight, and I want you to have feel the freedom to move through the video as quickly as you possibly want to. So each of these, feel free to hit that pause button, work it out yourself, and then compare it to my final answer. And if you agree with my answer, then by all means, just keep on chugging along. And if at any point you get stuck, I'll have the explanation here for you to kind of walk through and fix any sticking points you have. So if you want to, hit pause, otherwise keep her going here. The first thing I did on this one was I made like a beaver and I split, and I said cosine cubed divided by cosine squared is just cosine, and 4 divided by cosine squared is an interesting one. Instead of leaving it as 4 over cosine squared, I said, you know what, that's really 4 times secant squared. Instead of leaving cosine in the denominator, it's really a secant in the numerator. So now, integrating this term by term, the first term was just sine of x, and then we've got 4 times the tangent of x. We'll throw our plus c on there, and there's a beautiful answer. Alright, now we're ready to try out a U-sub. It's been a while since we've done these. This is one of those topics that as BC students we don't get a ton of practice with. We throw it at you and then it sits on the back burner for a while. But there's 3 different, I guess, main different U-subs we did. We started off like this one. We're going to let U equal the inner function and whatever's inside the radical in this particular case. There was also ones we'll see where we'll let U equal the exponent, and there are also times we'll let U equal the denominator. But this one's just pretty much straight up. We're going to let U equal the x squared minus 5. Make sure you do not include the radical in that statement. Our du is going to be 2x times dx. And as I solve for dx, we've got du over 2x equals that dx. And here's where all the subbing comes in. We got the integral of 3x times radical u, and then for that dx that we had originally, we're going to substitute and say du over 2x. So the good news is we could kill these x's. If there's ever a point where you can't kill all the x's, that's a really bad sign. And perhaps one of the more important things is, just handling these coefficients, and that's where a lot of the mistakes occur, and we fall in love with one of the wrong multiple choices. Also, I'm going to rewrite this as u to the 1/2 power instead of radical u. Now, my power rule says I'm going to add 1 to that exponent. I'm also going to divide by the new exponent, which is 3/2. But really, instead of dividing by 3/2, let's multiply by 2/3. Now, wait a minute. I had a 3/2 already. Now I'm multiplying by 2/3 because of the rule. And as I clean this up, I just have a coefficient of 1. So I've got u to the 3/2, which was really the quantity x squared minus 5 to the 3/2. And if you want to rewrite that as a radical, which would be a good idea, anytime the problem started in radical form, it probably should finish in radical form, and there's our answer. Oh, I'm not sure if this new screen with the black background is driving you nuts, or if you like it, or if you're indifferent. So if you're really excited or if you really hate it, let me know tomorrow in class. It was just a new option that came out as they updated the app, and I thought I'd try it at least once anyway. So here's another beautiful U sub. Now, we're not going to let U equal the inner function. Typically, our rule says that if you're doing an indefinite integral and there's an e in there, probably at least 90% of the time, you're going to end up letting u equal the exponent. That was our rule of thumb there for a few days in class as we learned this topic. So I'm going to let u equal 3x squared. And even in those 10% cases where it's not the exponent, I at least start with the exponent usually before I run into a dead end. Let's see, so du is really 6x times dx. Du divided by 6x is equal to dx. So we have the integral of x times e to the u times du over 6x. Good news here, we're going to kill those x's. That's fantastic. And just watch that coefficient here. We're going to slide out the 1/6. Do not lose that x or that coefficient. And then we got e to the u du. Oh, how we love e to the u, because his antiderivative is strictly e to the u. And if we rewrite our answer so it's in terms of x instead of u, we've got e to the, let's see, what was it? 3x squared plus 1. Throw our plus c. And this, ladies and gentlemen, is the answer to our indefinite integral. So hopefully you're cruising quite right along and you're building some confidence and you're feeling really good here. Now, here we have a contradiction of 2 of our rules. We had that rule that said if you see an e in your integral, you're probably going to let u equal the exponent. But we also had a rule that said if you're integrating a fraction, you're probably going to let u equal the denominator. And that one's going to be the one that works for this particular example. And you could always do this by trial and error. Here's another rule of thumb. How many times do you think you're going to let u equal x? That's my question. And I'm going to tell you probably never. So if that was your thought off the bat, I would say try to get away from that, because that typically isn't going to lead you anywhere prosperous, at least. Anyway, u equals the denominator, and then that means the derivative is going to just be e to the x dx. Solve for dx like we always do. And now we're ready to sub. Now my numerator is going to stay e to the x, my denominator is my u, and then I'm going to substitute for dx. Oh my goodness, how good does that feel? Got that beautiful cancellation. And now we are ready. Let's rewrite it as du over u. Antiderivative is the natural log of the absolute value of u plus c. And rewriting our answer in terms of x, we got natural log of 1 plus e to the x plus c. Now here's a question for you. Can I expand this one out? Can I use my log properties to maybe expand this one out and simplify it? Great question, right? The answer is no. All right. Can you expand the natural log of quantity a times b? Yeah, that's a great one. Natural log of a plus the natural log of b. However, can you expand the natural log of the quantity a plus b? And the answer is no. That one's completely done. There's nothing that you're allowed to do to that particular problem. Our last one for the night is perhaps the messiest one, where we've really got to just watch our, the sign of our exponent and moving things around from side to side, all that jazz. Here's a trick. I'm not going to let u equal the entire denominator, but I am going to let u equal the inner function, which in this case is 1 plus 2 radical x, or 1 plus 2x to the 1/2. My derivative is going to be 1 times x to the negative 1/2. As I solve for dx, tell yourself this rule. If I have a negative exponent on the right side, then I'm going to have that same term with a positive exponent on the left side. So this is really x to the positive 1/2. All right, as I solve for dx. And now, all right, let's rewrite it. So when I saw a dx up here, I'm going to substitute this into dx's place. So now I've got x to the 1/2 times du all over radical x, and then the u function that I had. So here's the good news. This bear kills that bear. Again, we've got the integral of du over u, and once you hit this moment, you can really celebrate, because you can see the finish line shortly ahead. We've got the natural log of u, and you're more than welcome to skip that step and go right here. The natural log of the absolute value of 1 plus 2 radical x plus c. Now, when I look at that problem, the part that I'm most nervous about it as your teacher is how you handled this particular phase right here in getting dx by itself, and just watching the sign on that exponent as you get dx by itself, making sure we get to a point where we can say with confidence that these two terms cancel each other out. So hopefully we are sky high and we're really dominating this particular topic, and we're ready to roll tomorrow.